In this video, I will review the phases of matter, their characteristics, and the various types of phase changes matter can undergo. By definition, matter is anything that has mass and volume. Depending on various factors like temperature and pressure, matter will exist in a particular physical state or phase. Depending on the source you look at, there can be as many as 7, 8, or even 9 possible phases of matter. However, many of these phases only occur at extremes of temperature, pressure, or energy, things like plasma and Bose-Einstein condensates. Therefore, we will only look at the 3 principal phases of matter: solids, liquids, and gases. Collectively, solids and liquids are called the condensed phases because they are actually more similar to each other than they are to the gas phase. We will explore this a bit more in the next few slides. Let us now look at each of these principal phases of matter and their characteristics individually. If we first look at the solid phase from a macroscopic viewpoint, how the solid phase of matter would appear to the naked eye, we see that solids have a defined shape and a defined volume. If we now move from the macroscopic and imagine zooming into the molecular level viewpoint so we can see how the atoms and molecules, or more generally particles, are arranged, we see that the particles are very closely packed together. This very close, rigid packing is because the interparticle attractions present are very strong. We will talk more about these interparticle attractive forces later. Because of these very strong attractions, the particles in a solid are locked in place and cannot move freely, but can only vibrate. Moving on to the liquid phase, the macroscopic view shows a phase of matter that has a defined volume but lacks a definite shape. Liquids will adopt the shape of their container. Zooming into the molecular level, we see that the particles are more loosely packed, but they are still touching each other. Liquid particles can freely move and slide past each other. It is this freedom of movement that allows liquids to flow or to pour. This more loosely packed arrangement is due to more moderate strength interparticle attractive forces. Finally, the macroscopic view of gases, or vapors, shows a phase that lacks a defined shape as well as lacks defined volume. Gases will expand to fill the shape and volume of their container. At the molecular level, we see that the gas particles are not touching at all and are quite widely separated. This wide separation is the reason we typically describe gases as being mostly empty space. As you might guess at this point, the interparticle attractive forces in gases are extremely weak, almost non-existent. Let's now consider a very familiar example: water, H2O. Water can exist in all of the principal phases of matter within a very narrow temperature range, 0 degrees Celsius to 100 degrees Celsius. If we were to begin with 10 milliliters of solid water, or ice, it will display a defined shape, like ice cubes, and it will simply sit at the bottom of the flask. If that same amount of water transitioned to the liquid phase, the volume would remain fixed at 10 milliliters, but the liquid water would take on the shape of the bottom of the flask. Finally, the gas phase would expand to fill the shape and volume of the flask. When a sample of matter is either heated or cooled sufficiently, it will undergo some type of phase transition from its current state to a different phase of matter. There are a total of 6 possible phase transitions. These 6 phase transitions exist as 3 pairs of related transitions, where one is the reverse of the other. Let's now look at the various types of phase transitions that are possible. The solid to liquid phase transition is melting, and the reverse transition from liquid to solid is freezing. Beginning with the liquid phase, the transition to the gas phase is vaporization, and the reverse transition from the gas phase to the liquid phase is condensation. When a solid transitions directly to the gas phase without melting first, the phase transition is sublimation. The reverse of sublimation, the transition of the gas phase directly to the solid phase without condensing, is called deposition. In order for a phase transition to occur, some amount of energy will need to be gained or lost. In general, the solid phase is the lowest energy phase of matter, and the gas phase is the highest energy phase. The energy of the liquid phase is somewhere in between that of the solid and gas phases. However, the energy of the liquid phase is not exactly in the middle. Liquids are energetically more similar to solids than they are to gases. If a liquid were to transition to the gas phase by vaporization, energy would need to be absorbed in an endothermic process because the transition was from a lower energy phase of matter to a higher energy one. If the gas returned to the liquid phase by condensation, energy would be released in an exothermic process because the transition was from a higher energy phase to a lower energy phase. It is important to note that the quantity of energy needed to vaporize a sample of liquid is the same as the quantity of energy released when the gas condenses back to the liquid state. The only difference is the direction of energy flow. A similar argument could be made about the sublimation-deposition pair of phase transitions. Energy would need to be absorbed in order for sublimation to occur, and then energy would be released for deposition to occur. To put this in other terms, the delta H of vaporization, or the heat of vaporization, we've said is an endothermic process, and recall that endothermic processes have positive delta H values. The delta H of condensation, we've said, is an exothermic process, which have negative values. If the quantities of energy are the same, and one has a positive value and the other has a negative value, we could say that the delta H of vaporization is equal to the negative of the delta H of condensation. To summarize, matter exists in one of three principal phases: solids, liquids, and gases. The primary difference between the phases is the strength of the interparticle attractive forces present. Conversion of matter from one phase to another is called a phase transition. There are 6 phase transitions possible in 3 pairs of related phase transitions. Transition from a lower energy phase to a higher energy phase requires energy and is thus an endothermic process. Transition from a higher energy phase to a lower energy phase releases energy and is therefore an exothermic process. Thank you for listening.